Thank you for the presentation. And can I start here?
Yes, yes.
Okay. Thank you for the presentation and good morning, everyone. So in the following presentation, I talk about on failure analysis in heterogeneous and homogeneous structure. This work is co-authored with Professor Lonetti and Pascuzzo Greco and Dr. Lonetti at Pascuzzo. So, in the recent years, the notable advance in computational files have permitted using several numerical methods able to reproduce crack propagation phenomena which affect new or existing materials for engineering application. So, the fracture mechanics employ the continuum mechanics employ fracture and damage model, such as linear lattice fracture mechanics or coexistence model, or continuous damage mechanics or phase field methods, together with numerical models, like, for example, finite element method with and without remeshing, or extended finite element method, etc., to model discontinuous deformation. So, fracture is a common failure mode of engineering materials and structure, and preventing failure caused by crack is a significant concern in engineering design. Like in many other physical phenomena, computational modeling of fracture is an essential tool for providing knowledge into the fracture process of various materials, such as concrete, metals, nanomaterials, and etc. And the numerical simulation represents an effective tool to ensure assess the structural integrity, especially when full-scale experiments may be too expensive or replicable. And in addition, developing advanced numerical approach that ensure a suitable compromise between computational cost and good prediction is attracting considerable attention from the international research community. And for this reason, in this work, we present an efficient cohesive phase field model within a finite element framework for actually reproducing crack propagation phenomena in both homogeneous and heterogeneous structure. In particular, the proposed approach enhances the traditional phase field approach, known for its effectiveness in simulating integrated fracture patterns with the adaptive mesh technique to reduce the computational demands posed by, for example, heterogeneous materials. So, an overview of the cohesive phase field model proposed by you is now presented. In general, the phase field model replaced the sharp crack interface with a diffusive interface, characterized by a crack phase field variable, PC, which evolve between 0 intact material and 1 fully cracked material. The crack surface density function is central to the formulation, is expressed in terms of PC and its spatial gradient. Here appear also the length scale L0, which regularizes the sharp crack, and the crack geometry function alpha, who define whose the material stiffness degraded as crack bolts. The parameter psi control the regularization model behavior, and it range between 0 and 2, and who model psi is equal to. The governing equation in quick form for crack propagation problem is the following, where H is the history variable and W represents the energy degradation function, and which are evaluated through the following expression. So the function W is dependent also on 3 parameters, A1, A2, and A3. In particular, A1 is calculated via this formula and depends on both length scale L0 and characteristic length LC, while I2 and 3 depend on the softening curve. So this slide compare linear, exponential, hyperbolic, and Cornelius softening curve obtained by U with the analytical one. For each type of softening curve, we have reported the analytical way, the analytical law, sorry, and the expression of K0 and WC, which represent the initial slope and the ultimate crack opening displacement, which respectively. So in In the slide, appears of the exponent t, which appear in the function W, which assume this value in order to obtain the correct value of W to C. The approximated of the curve obtained by U coincides with the analytical one for linear, exponential, and hyperbolic softening, but showing a slight discrepancy from analytical one. The adaptive mesh technique is now presented, emphasizing its crucial role in the proposed approach for improving computational efficiency by focusing mesh refinement only in the region where damage nucleation and propagation are expected to occur. So the key elements or the adaptive mesh technique is essentially three. The first is a construction of divided the computational domain into a grid of macro elements. The second is to remove the macro elements within a zone of interest, which must contain the expected location of the damage nucleation. And the third is to choose appropriate set criterion, which define where and when defined mesh should be introduced. So this criterion is based on the damage characteristic field variable at micro-macro interface. So this slide reports also the concept of micro-macro connection for non-matching mesh, which is a technique employed to handle a situation where different mesh types are used in different parts of the structure. In particular, this technique, through the collocation method, ensure continuity between two different mesh, imposing that the displacement jump between the micro and the macro interface is equal 0 for each for every weight function delta lambda. So the cut propagation process is managed by an automatic algorithm. The analysis starts by defining geometry, material properties, and boundary conditions. So the computational domain is divided into a macro subdomain, and within a zone of interest, micro subdomain are inserted. So at the interface between micro and macro subdomain, continuity conditions are imposed to ensure that the transition between two different mesh does introduce artificial discontinuity on displacement files or stress. At this point, the analysis starts by increasing control displacement. For I forget things. In the macro subdomains are measured with a single finite element, while the micro subdomain are discretized using a finite mesh. After that, the analysis starts increasing by increasing the control displacement, and for the code for each increment, check the damage condition at the micro macro interface. So the interface where the crack damage variable is greater than a set threshold is marked at a critical micro macro interface, and adjacent macro subdomain is marked as a critical macro element. Once a critical macro element is found, it is detected, and the damage fine mesh is inserted in this region. Finally, the code checks if the structure reaches the failure. If the total failure occurs, the analysis stops. If not, the process continues, refining the other region as the damage progress. So now, to verify the efficacy of the present method, two crack problems are presented. The first is a mixed mode failure test of a notch concrete beam having the following material property, and Cornelis software curve are employed to capture the material degradation the material during the crack propagation. So the zone of interest consists of 4 microsubdomains, and the mesh of a single microsubdomains involve 217 nodes and 3,912 reachable elements. The slide reports a comparison in terms of load versus crack mouth open displacement between the present method, the experimental data, and the prediction provided by other numerical strategy. We can see that the obtained curves are in good agreement with the experimental data and the numerical results provided by who, thus denoting the reliability of the present method for predicting characterization, propagation, and failure. In addition, we can see the snapshot of the damage profile during the 3 steps of the propagation. Now, comparison between non-adaptive and adaptive scheme are reported for evaluating the computational efficiency of the present method. Note that to reproduce the non-adaptive scheme, the microsubdomains are activated at the beginning of the simulation. This slide demonstrates the advantage of the adaptive scheme. In fact, the non-adaptive and adaptive curve for load versus crack mouth open displacement are almost the same. And this is denoting that the adaptive scheme does not compromise the accuracy of the simulation. So, in addition, the adaptive approach provides a more efficient simulation, because it's significantly reduce the computational time with a reduction of about 68%, and the number of cumulative degree of freedom with a reduction of 70%. So this occurs because we can see from crack growth evolution, the final mesh configuration, the adaptive scheme dynamically refine the mesh only in the region where crack propagation takes place. The second example involves a 3-point bending test of a perforated beam with an eccentric crack. Starting with the geometric of macroscale domain, the beam has a length of 140 millimeters and an height of 80 millimeters. On the right side, instead, we say the geometry of the microscale domain, where each perforated microstructure or microsubdomains consists of a square shell with a centered hole. So the elastic and the phase field property are the following. And in this case, exponential softening curves are used to capturing material degradation during the crack propagation. And in this case, the fine mesh of the microsubdomains involve 187 nodes and 318 nodes. So the animation of the damage profile during the propagation show the ability of the proposed method to refine the mesh only in the region where this is necessary. So the zone interest consists of 5 microsubdomains. It's important to say that homogeneity moduli are used in the macro elements to account for the presence of the hole. Also, in this case, a comparison in terms of load versus displacement of the midpoint of the beam between the present method and the numerical result provided by Coy and Sadat are reported. And also in this case, the obtained curve is an excellent and a good agreement with the results taken as a reference. So here we can see instead the snapshot of the mesh configuration during the crack propagation. Also for this example, we report the comparison between non-adaptive and adaptive scheme. The slide show also in this case the advantage of the additive scheme. In fact, there is an improvement on computational efficiency compared to the previous case. In fact, the computational time have a reduction of about 91%, and also the number of relative degree of freedom. These results make the proposed adaptive approach more suitable for complex crack problems where computer efficiency is crucial. So, in conclusion, an efficient finite element adaptive phase field model for reproducing the crack propagation phenomena in both homogeneous and heterogeneous structures proposed, which enhance the traditional phase field approach by incorporating an adaptive mesh technique, allocating computational resources only where necessary, thus improving computational efficiency while maintaining accuracy. The proposed method has been validated through comparison with experimental data and numerical results, thus denoting that this strategy ensures accurate prediction. And in addition, despite non-adaptive phase field approach, the proposed model significantly reduces computational burdens in terms of computational time and the total number of degree of freedom. So the future perspective of the proposed work include the extended in a 3D setting and enhancing its capability to model more complex failure mechanisms, and including interfacial debonding in fiber reports composite. Thank you for your attention.